One of the most important applications of the derivative is in determining instances when a mathematical model of a natural phenomenon yields a maximum or minimum. Such process is popularly called optimization. In this video lesson, you are expected to use the extreme value theorem in finding the maximum and minimum value of a given function at a given interval, and in solving optimization problems, and solve the derivative of a composite function using chain rule. Before we proceed to lesson 1 proper, we have to recall some rules of differentiation and how useful they are in finding a derivative of the function at a number. Instead of using the long process of the alternative definition of the derivative, we can simply use the applicable rules directly. For instance, in this function f, for us to get the first derivative of the function at number 2, we have to differentiate first the function using the constant rule, power rule, the constant multiple rule, as well as the addition and subtraction rules. By using those mentioned rules, the derivative of the function f is equal to 2x minus 4, and by substituting x by 2, we have 2 times 2 minus 4 is equal to 0. On the left is the picture of your answer using the alternative definition of derivative. Primarily, the goal of lesson 1 is to use the extreme value theorem in finding the maximum and minimum value of a given function at a given interval. The extreme value theorem. Let f be a function which is continuous on a closed unbounded interval ab. Then the extreme values, the maximum and the minimum of the function f always exist, and they occur either at the endpoints ab or at the critical points of the function f. When we say minimum, this is the lowest value of the function. Maximum, on the other hand, is the highest value of the function. And when we say critical point, these are the values of x that will make the derivative of the function equal to 0 or undefined. Here are the steps in finding the extrema of the function. First, get the derivative of the function f. Second, get the critical points inside the interval. To get the critical points, we will just simply equate the derivative of the function to 0. Third, get the functional values. These values are the two endpoints of our interval and the critical points inside the interval. And lastly, compare the values. Find the extrema of the function f of x equals 2x cubed minus 6x on the closed interval 0, 3. By using the graphing application, this is the form of the graph of the function f. And if we will zoom in the function at the interval 0, 3, at x equals 0, the functional value is 0 because of the coordinate 0, 0. At x equals 1, the value is negative 4. And when x is equal to 3, f of x is 36. If you click the tools, choose the box extrema, and we get a coordinate of 1, negative 4, which means that the minimum value of the function f is negative 4. How about the maximum? Of course, if we will consider the entire graph, its behavior is that it goes to positive infinity. Since we are only within the bound of 0, 3, then at x equals 3, f of x is 36, and that is the maximum. Algebraically, we have to follow the 4 steps. The derivative of the function f of x is equal to 6x squared minus 6. Next, we will get the critical points inside the interval by equating the derivative of the function to 0. 6x squared minus 6 equals 0. By simplifying, we have x equals positive and negative 1. We have 2 critical points. We consider only positive 1 because at the interval 0, 3, negative 1 is out of bound. For step 3, we will get the functional value of the endpoints of the interval 0 and 3 and our critical point positive 1. By using the original function f of x equals 2x cubed minus 6x, we will evaluate the function at 0, 1, and 3. At f of 0, the value is 0. At f of 1 is negative 4, and at f of 3, that is 36. Next, we will compare the values of this function. Therefore, the maximum of the function occurs at x equals 3 with a value of 36, and the minimum of the function occurs at x equals 1 with a value of negative 4. These values coincide with the graph presented earlier. In this part, you are expected to use the extreme value theorem in solving optimization problems. Again, when we speak of optimization, we are referring to the maximum or the minimum function value. Here are the suggested steps in solving optimization problems. For example, find the number in the interval negative 2 to positive 2 so that the difference of the number from its square is maximized. From the keyword, the difference means subtraction. Suppose we have a number positive 2. Since this is about the difference of a number from its square, so we will square positive 2, so that is 2 squared. Subtract it from the word difference by the number 2, and in that case, our answer is positive 2. In this problem, we need to get the number that will yield the highest or the greatest functional value because of the term maximize. Since the number is unknown, so we let x be the desired number. And from the problem, that is the square of the number minus the number itself. And because of the interval negative 2 to positive 2, our x must be an element of that closed interval. F of x equals x squared minus x is a polynomial function. And it is a known fact that polynomial function is continuous everywhere. Hence, the extreme value theorem can be applied in this problem. We will now follow the fourth step. First, we will get the derivative of the function f of x equals x squared minus x, and the derivative is 2x minus 1. For step 2, we will equate 2x minus 1 to 0. The value of our x is 1/2. We have only one critical number, and it is within the bound of negative 2 to positive 2. For step number 3, we will compute the functional value of the endpoint negative 2 and positive 2 and the critical number 1/2. From the original function x squared minus x, if we will change negative 2 to x, we have positive 6. For f of 1/2, we have negative 1/4, and f of 2 is positive 2. By that, we generate the table of values on step 4. We conclude that the function attains a maximum on the closed interval negative 2 to positive 2 at the left endpoint x equals negative 2, because the value of the function is positive 6, which is the highest. Hence, the number we are looking for is negative 2. This can be affirmed by the graph as shown on the lower left. For the second problem, a rectangular box is to be made from a piece of cardboard 24 cm long and 9 cm wide by cutting out identical square from the four corners and turning up the sides. Find the volume of the largest rectangular box that can be formed. Since this is a rectangular box, then we need to compute the volume of the box, and the formula is length times width times height. When can we have the largest rectangular box from this dimension? That is, if the volume is the greatest or the maximum. According to the given, the dimension of the box is from the cardboard with the dimension 24 cm and 9 cm. Since we will cut identical square from the four corners, so the dimension of this part is s, and so with this is s, since this is a square. By that, our length now, since we cut s unit from this side and so we this side, so our length now becomes 24 minus s, or simply 24 minus 2s. For the width, since we will cut s unit here and s units here, then this is now equal to 9, which is the original given, minus 2s. After cutting this square, then we will turn up the sides, and this will be the form of the box. The height of the box now is S. With that, we can compute the value of the box by multiplying the length, the width, and the height. So we will now compute the volume of the rectangular box by substituting the value of the length, the width, and the height. For the length, we have 24 minus 2s. The width is 9 minus 2s, and the height is s. Multiplying these two binomials, so we generate this one, and this is equal to 216 minus 66s plus 4s squared. And this product will be multiplied to s. So s times 216 is 216s. S times negative 66s is negative 66s squared. And s times positive 4s squared is positive 4x cubed. So that is now the equation of our volume with respect to the side s. Observe now the possible value of s. Our s should not be non-negative number and should not be more than half of the width of the cardboard. That is, s should be an element of the closed interval 0 to 4.5 because 4.5 is half of the width given, which is 9 cm. Since the function v is polynomial, then it is continuous on the closed and bounded interval 0 to 4.5. Thus, the extreme value theorem applies. This time, we are going to show the 4 steps in finding the extrema of this function. For step 1, we will get the derivative of the function v. So this is the function v. So the first derivative is 12s squared minus 132s plus 216. We will now factor the common. So the common of these terms is positive 4. So we have 12s squared divided by 4 is 3s squared. Negative 132s divided by 4 is negative 33s. And positive 216 divided by 4 is 54. And we can still factor this trinomial. So we have 3s times s. We will get now the factor of 54 such that if we will get the inner and the outer product, the answer is negative 33s. So factor of 54 is negative 9 and negative 6. And if we will get the inner and the outer product, so this is negative 6s, and this one is negative 27s. Negative 6s and negative 27s is equal to our middle term, which is negative 33s. So this is now the factored form of the first derivative of the function v. For step 2, we will equate this derivative to 0. So one by one, we will equate the product to 0. So the first one is 4 times 3s minus 6. This is equal to 0. So we will divide both sides by 4. So that becomes 3s minus 6 equals 0 divided by 4 is 0. And additive inverse of negative 6 is positive 6. Dividing both sides by 3. So the s is positive 2. And for the second factor, s minus 9 equals 0. Additive inverse of negative 9 is positive 9. So in this case, we have two values of s, which is positive 2 and positive 9. Since we have two critical numbers, we have to check which of these is within the bounded interval 0 to 4.5. And that is only s equals positive 2. So our critical value in this problem is only s equals positive 2. And for step 3, we are going to evaluate the functional value of the two endpoints and one critical value, which is positive 2. Using the original equation, so for s equals 0, the value of the function is 0. For s equals positive 2, the value of the function is positive 200. For s equals 4.5, the value of that function is also 0. And this is the graph of the function v. It is visible on the graph that at x equals 2, the function is at the maximum value of 200. Therefore, based on the table of values and on the graph, we see that v attains its maximum at s equals 2, and the maximum volume is 200 cubic centimeter. The last part of the lesson is on solving the derivative of a composite function using chain rule. Also, the higher order derivative shall be discussed and presented here. What we have discussed so far as the derivative of the given function is sometimes referred to as the first derivative and is also a function. Thus, it follows that we can also obtain its derivative, which we call the derivative of the derivative or simply the second derivative. Now, the second derivative being a function gives us an opportunity to also get its derivative, which is called the third derivative, and so on. We have to follow the rules in differentiation on this matter. For the given function f, 2x cubed minus 3x squared plus 10, so the derivative of the function or the first derivative is equal to 6x squared minus 6x. Since this is a function, we can still get the derivative of this derivative. For the second derivative denoted by the double apostrophe, from the first derivative we can derive the second derivative, and that is 12x minus 6. For the third derivative is equal to 12, and for the fourth derivative that is equal to 0. This is the theorem that relates to the chain rule. Let f be a function differentiable at c, and let g be a function differentiable at f of c. Then the composition g compose f is differentiable at c, and the derivative of the g compose f of c is equal to the product of the derivative of g of f of c and the derivative of f of c. In other words, the derivative of a composition of functions is the derivative of the outer function evaluated at the inner function times the derivative of the inner function, or the dy over dx equals dy over du times du over dx. In our first example, find the second derivative of the function f of x equals the square of 3x squared minus 2x plus 4. In this given, we will let this one as u. So our f of u is equal to, since this is u, then this is u squared. So your f of u is u squared. And the derivative of u squared is 2u. And the value of our u, which is this, is the trinomial 3x squared minus 2x plus 4. And the derivative of this function is 6x minus 2. By using this formula in the chain rule, so we have the derivative of y is 2u, this one. And the derivative of u over dx is 6x minus 2. We will now substitute u by this trinomial. So we have 2 times this trinomial times 6x minus 2. Distributing 2 to this trinomial, so we have 6x squared, negative 4x, and positive 8 times 6x minus 2. Multiplying these two factors, we have this one. Combining like terms, so we have 36x cubed minus 36x squared plus 56x minus 16. So this is still the first derivative of the function. Since we are looking for the second derivative, then we will get the derivative of this derivative. Find the derivative of y if y is equal to sine 2x using the chain rule. So we will let u equal to 2x. So this one is in the form sine u. And the derivative of sine u in the trigonometric equivalence is cos u. And the value of our u is 2x, so the derivative of 2x is 2. Using this formula, dy over du is cos u times the du over dx is positive 2. Multiplying this one, we have 2 cos u. And substitute u by this expression 2x. So the answer is 2 cos 2x. So the derivative of y of x is 2 cos 2x. If y equals square root of x cubed minus 7, find y prime using the chain rule. If we will change this radical form into an exponential form, this one is equivalent to x cubed minus 7 raised to power 1 half. So this one will be our u, so we have u power 1 half. So the derivative of u power 1 half is 1 half u. This exponent minus 1. So that is equal to 1/2 u. 1/2 minus 1 is negative 1/2. Our u is x cubed minus 7. And the derivative of x cubed minus 7 is 3x squared. Using this formula, we will just apply the substitution. So dy over du is 1/2 u power negative 1/2. This one times du over dx is 3x squared. Substitute u by x cubed minus 7. So we have this power negative 1/2. We will get the reciprocal of x cubed minus 7. So that is 1 over x cubed minus 7, and the exponent now is positive 1/2 times 3x squared. We will now transform this to radical expression, so that is equal to 1 over square root of x cubed minus 7. Multiplying the numerator, 1 times 1 times 3x squared, so we have 3x squared. And the denominator, 2 times the square root of x cubed minus 7. Chain rule is also used to find the derivative of the power function of x. That is, the derivative of x of f of x power n. To derive a formula for this, we let y equals u power n, where u is differentiable function of x given by u equals f of x. Dy over du, the derivative of u power n is equal to n times u. The exponent will be subtracted by 1, so we have n minus 1. And for the derivative of the function f of x, we will just simply use the f prime of x. By using the formula of the chain rule, dy over du is this one, n times u power n minus 1. And du over dx is the derivative of the function f. We will now substitute u by f of x. That becomes n times the function f of x power n minus 1 times the derivative of the function f. This one is called the generalized power rule. What is the derivative of y? Equals the fifth power of 3x squared plus 4x minus 5. The derivative of this function is equal to, copy the exponent 5, the function, copy the function, raise 8 to the original exponent minus 1 times the derivative of that function. And the derivative of this function is 6x plus 4. So this is now the derivative of the function y. In order to use the generalized power rule, we need to have an exponent of the function. This is a radical form, changing radical to exponential. So this one, by using the formula of the generalized power rule, we will just copy the exponent, copy the function, the original exponent subtract by 1, and the derivative of the function, 3x cubed plus 4x plus 1. 1/2 times the function, 1/2 minus 1 is negative 1/2. Now we will get the derivative of this function, and that is equal to 9x squared plus 4. Get the reciprocal, use positive exponent, changing that to radical expression, and multiplying numerator by numerator and denominator by denominator. So we have 9x squared plus 4 all over 2 times the square root of 3x cubed plus 4x plus 1.